Hi, my name is Michelle Tommen, and I am giving my final presentation for CIS 4930, Top 10 Algorithms, under the guidance of Dr. Locker. And I'm giving my presentation on hypergraphs, which I became interested when we were studying graph algorithms and Kevin Bacon. Hypergraphs are a generalization of graphs, and that generalization can have benefits, especially in the realm of data representation, knowledge representation. It's also good for a lot of combinatorics problems, and we're starting to learn that for specific kinds of hypergraphs, that performance is actually better than if the data were represented as graphs. So the formal definition of a hypergraph is similar to the one for a graph. H is equal to the tuple, set of vertices, set of edges. The difference is that these edges are hyperedges, and which means that each edge is any subset of V. Another way to say that is E is a subset of the power set of V, not including, of course, the empty set. And so we can see from this that a graph is a hypergraph. It's just the special case where every single edge has the cardinality 2. It's just a tuple of vertices. Alright, so yes, it is a very general structure, and very, is very basic in terms of mathematics. How do we draw a hypergraph? Well, for an undirected hypergraph, the best way is with something that looks like Venn diagrams. So if these are our vertices, then an edge, let's say an edge that is equal to the vertices 1, 2, and 4, the set of vertices 1, 2, and 4, would just look like this. It would just be a closed plane enclosing those. And let's say we'll call this edge 1, let's say we have another edge closing those. We'll call that edge 2. Let's say this is edge 3, and we'll say this is edge 4. Alright, and I'll note here that if I had included in edge 3 4 also, that would mean each edge was a set of 3 vertices. That would be considered a uniform hypergraph, specifically a 3 uniform hypergraph. But since this edge has only 2 versus the 3 nodes in the other ones, it is non-uniform. Alright, so how do we represent this on the computer? The best way is probably with a matrix, and where the columns are vertices and the rows are vertices and the columns are edges. And so in this hypergraph we've got vertices 1, 2, 3, 4, 5, 6, 7, and we have edges E1, E2, E3, and E4. Alright, so what is each entry? Well, if an edge includes the vertice as a member in its set, then you'll have a 1. And if it doesn't, then a 0. So for E1, E1 is the set of vertices 1, 2, and 4. So we'll put 1s there, and then 0 for everything else. E2 is the set of vertices 4, 5, and 7. So put 1s there, and 0 everywhere else. E3, 1 and 3. 0s everywhere else. And E4, 4, 6, and 7. 0s everywhere else. Alright, and we can see from here that, that if we look across a row, so let's say we're looking at vertex 4, the row for vertex 4, we can see each edge that contains 4. If we're looking down a column, we're looking at every vertex in an edge. Alright, and I'll note here that one popular area of research is finding minimum transversals, which is trying to find the minimum set of vertices such that the vertices intersect with every single edge. So in this example, a minimum transversal is easy to find. We can see that vertex 4 is in E1, E2, and E4, so that takes care of those 3. E3, we can pick either E1 or 3, so we'll pick 1. So just using the vertices 4 and 1, we can get to every single edge. So just wanted to know that's a popular area of algorithm research, is trying to find that minimum transversal. Alright. Alright. So that hypergraph was very general. Let's get a bit more specific. Let's work with directed hypergraphs. And so a directed hypergraph is where an edge is the tuple, the tails of the edge and the heads of the edge, and where T is just a subset of vertices V, H is a subset of the vertices V, is any subset. And how we can represent a directed hypergraph is actually different. A better way to represent directed hypergraphs is not with the Venn diagram, but by having arrows that connect. So this is actually only one edge. We'll call this E1. So E1 has as its tail 1, 2, and 3, and it has as its head 4 and 5. So let's continue with this. So I created 2 more edges. This edge 2 connects 1 and 4 as the tails to 8 and 6 as the heads, and then here's edge 3, which with 7 and 8 as the tails and 5 as the head. So how do we represent that with a matrix? We still have the vertices listed on the left. and we have our edges across. E3. The difference is that our entries, A, I, J, will be a negative 1 if the vertex is a tail of the edge, a positive 1 if it's a head, and 0, of course, if it's not in the set of the edge. Alright, so for this example, for edge 1, we've got 1, 2, and 3 as the tails. That's negative 1 as the entries there, and then the heads 4 and 5, positive 1, and then zeros everywhere else. Alright, for edge 2, we've got 1 and 4 as the tails, and we've got 6 and 8 as the heads. And then edge 3, we've got 7 and 8 as the tails, and the head as 5 and zeros everywhere else. Alright, and so you can see that when we look across a row for a specific vertex, we can see what it's a head or tail of. We can see that 1 is a tail of 2 edges. We can see that 5 is a head of 2 edges. We can see that 7 is only a tail. And what we'll call a directed edge, we'll call a hyperarc. I will use that term from now on, hyperarc, for directed edge. Alright, so this is a specialization of hypergraphs where it's directed. Now let's get even more specific to where we're getting to even more useful types of hypergraphs. The first type of hypergraph that is very useful is a directed graph where the heads of each edge has cardinality 1. So that would look like this. So there can be at 1 or more tail, but there can only be 1 head. Alright, so as you can see, these all converge onto one. Multiple nodes as tails will converge onto one head. This is a good example of why these graphs, which are called B graphs for backward graph, because these are B hyperarcs or backward hyperarcs, these are good for situations with deduction. You know, given these 3 nodes, we can deduct this node. Given these 2 nodes, we can deduct this single node. Alright, so again, this type of graph is called a B graph, and it has 1 head, and it is good for deduction. Alright, and the alternative to that is an F graph, or forward graph, because it has forward arcs, and those have only 1 tail. So given that same graph, alright, we've got this as the tail going to these 2 nodes. We've got this as the tail, this tail goes to these 3 nodes. Alright, this as the tail, we'll say, goes to those 2 nodes. Alright, and so this type of graph, the F graph, is good for representations of implication. Because we're saying that this node implies these 2 nodes. This node right here implies these 3 nodes, which are its head. And so these 2 types of graphs are studied a lot, and again, they're very good for situations of deduction and implication. And these 2 graphs are the types I used in the application I developed. And specifically, I used a BF graph. BF graph, which is a graph that has B hyperarcs or F hyperarcs. So, which means that it has both deduction and implication in it. And the application I developed is a knowledge base. A knowledge base is just a representation, a storage representation of knowledge. And it's used in a lot of different areas, especially artificial intelligence. Because we are trying to represent lots of data, lots of different types of data, and especially lots of unstructured dynamic data. And that's a big problem because computers currently require a lot of structure in order to store information, and unfortunately all dynamic knowledge is not very structured, so people have to force knowledge into structured storage, and we're researching ways that we don't have to do that. And a good structure are graphs, and especially hypergraphs, and because as we'll see, they're very good for showing. It's very good for clearly showing relationships between objects. In the knowledge base that I am proposing, I propose 2 different types of objects and only 2 different types of relationships. Usually when we represent knowledge with graphs, each edge represents a type of relationship between the 2 nodes. So let's say we've got a social media graph, and we've got Sarah, Bob, Lucy. Now we might have an edge here where these edges represent knows. So that's saying Sarah knows Lucy, Lucy knows Sarah. All right, but so that's the type of edge this is. This is a knows edge. And then we could have a totally different edge called likes. So Sarah likes Bob, but then we'll say Bob likes Lucy. We'll have a little love triangle there. All right, so that's traditionally how a lot of graphs have represented knowledge. I propose with a hypergraph that we can represent all knowledge with only the relationships is A and has A. scientists will recognize these two relationships. We use them a lot with representing data, such as perhaps a table in a database has certain attributes, or a database is a subset of another type of database. We also have it with classes. A class has its members, it has instantiations of objects, or a class is a subset of another class. It inherits qualities from another class. And I propose that all knowledge can be represented with only these two relationships if you also have two types of objects. And those two objects are a property value pair. So property colon value. And we have a lot of markup languages that use this same sort of scenario where you'll have a tag and then the value between those tags. So an example of a property value object might be color. And an object is represented with brackets. So an object might be color white. All right. And this has a relationship, must have on its right side, so blank has a, and then it must have this type of object, a property value object. So what that's proposing is that objects only have properties, a property value, versus the other type of object, which is a class of objects. So this is more like a concept of objects. With this example of color white, the class of objects would be color. And this type of object can only be on the right-hand side, is on the right-hand side of the is a relationship. What I mean to say is the is a relationship can only have on its right side a class of object. Alright, so again, I propose that all knowledge can be represented with these two relationships, is a and has a, and these two objects, which is property value or class of objects. Let me give you a few examples that hopefully argue that this is possible. All right. So let's use as our example, let's use movies and actors. Let's start with Jim Carrey, the actor. And again, I had proposed that there's only the two types of objects, class of objects and a property value pair. Jim Carrey is not a class of objects. He's a person. So he must be a property value pair, which the property of Jim Carrey is that he is a person. Now this is a very philosophical choice. There's a school of philosophy that says that all we are, all that things are, all that objects are just a collection of properties. And so I'm choosing that route in this knowledge representation, and saying that Jim Carrey is not itself an object. Jim Carrey is person : Jim Carrey. You could also have actor Jim Carrey. So, this is Jim Carrey as the actor. But how are these two related? Well, actor has a property of the person Jim Carrey. That is a property of it, and this fits our constraint that as a head of the has a relationship has to be a property value object. The actor Jim Carrey can have other properties. Perhaps we say he also has a. Actually, I'll start from here. He has a famous trait. Which is, his famous trait is like rubbery limbs. Right? He can also have another famous trait. Which are maybe his facial expressions. Alright, so as you can see here, we have a certain type of hyperarc, which is the F hyperarc. Because we only have one tail and multiple heads. And so this is actually going to be a constraint. The has a relationship must be a hyperarc. So any object that has other objects, which are property value pairs, can only have one has a relationship that is an F hyperarc. And again, the F hyperarc shows implication, which is to say that actor Jim Carrey implies these three those three properties. We then have our is a relationship, which we can use here. Person Jim Carrey is a person. Alright, you'll notice that person is the the property of the property value pair. And really any property value pair is a property, whatever property is on the left. So actor Jim Carrey is an actor. Famous trait rubbery limbs is a famous trait. And that logically makes sense because person Jim Carrey is an instantiation of a person. Famous trait rubbery limbs is an instance of a famous trait. And this is a relationship is exclusively a B hyperarc. Alright, which means that it can have multiple tails but only one head. So what else could be a tail to the object person via an is a relationship? Well, we might have person, me, Michelle Tom. And so I will be connected to that same arc. We could also have person, I'll say another celebrity, Jeff Daniels. And that will also be connected to that is a hyperarc. So this is a hyperarc. This hyperedge belongs to person. It's the is a hyperedge of person. And from it we can see all by starting at person and looking at the tails of the is a relationship to it, we can see all instances of person. Here, via the has a relationship, we can see all the properties that actor Jim Carrey has. Alright, so you can imagine this can quickly get huge, because we can say person Jim Carrey has a property, and of course he can have multiple properties because it's an F hyperarc. And really they're all the properties that any person can have. So he can have an eye color, which I think we'll say are brown. He can have a birthplace, which he is Canadian. He can have a home address. Alright, which might be just 123 4th Street. Alright, and of course each of these has an is a relationship. Eye color, brown, is a eye color. Birthplace, Canadian, not Canadian, Canada, is a birthplace. Home address is a home address. We could even say actor Jim Carrey has a property of an office address of 45 Terrace Road. Alright, and let's say we want to somehow compare these two, because they're both types of address. Well, how do we connect them? Well, what we would do is we have another has a relationship where office address has a address. Or, I'm sorry, office address is a address. And of course there would be one more is a there. Office address is a office address, which is a address. Same as home address. We would say home address 123 4th Street is a home address, which is a address. Alright, so by getting to this node, we can see that instances of it are office address and home address, and then we can see that an instance of home address is Jim Carrey's home address, or if we're looking at office addresses, we can see that an instance of it is the actor's office address. Let's see. So anyways, you can see that this can get very large, lots of different types of information can be included. There's no domain constraint. The domain is universal. And I think it's useful to have a universal domain, especially for artificial intelligence, because it allows the computer to make connections between anything. And to see anything in different types of contexts. You're never really predefining what something is. You're showing how something is related to other objects, and then the computer only needs to walk the path between all those relationships between the objects, to understand the world around it. And I'm not sure how those statements of, actor Jim Carrey is a actor, what exactly is feeding that to the artificial intelligence. Perhaps some sort of expert is entering those facts. But the data does need to be represented in that form of object is another object, but where this object is class of objects. And then object has a property value pair. Alright, and again, these are both objects, so those can be either of those can be on the left-hand side of either type of relationship. But anyways, a bunch of statements will get entered, and then we have something that parses that statement, where this is considered the node, this is the relationship, this is the tail, and this is the head node. And let's see, so once that statement has been parsed, all the statements have been parsed, they get put into a matrix. And it could be one huge matrix that includes both is a and has a edges as the columns, but I'm going, especially for the clarity of this presentation, I'm going to split it into two matrices, which is going to be, this is our is a, where each edge is going to be an is a, and then over here is our has a, where each edge is a has a. I'm going to make this a little smaller. And then our rows, of course, our columns are, these are our objects. So this is showing us that we can divide the hypergraph into two distinct matrices. It may be beneficial to have them combined as one matrice for easier parsing, but this is good at least for clarity. So let's go back to our example of having actor Jim Carrey. Alright, and we had already said that actor has a property of a person, which is Jim Carrey. So that's going to go in our has a table, and our tail is going to be actor Jim Carrey to person Jim Carrey. Alright, and if you remember, the has a can only have one tail. So this edge right here, which we'll just call edge 1 for now, is defined by this tail. Again, because it can only have one. So this actor Jim Carrey, it can have multiple properties, which will all be positive ones, but it only comes from one actor Jim Carrey. So again, over here, this is defined by the tail. Over here on the is a, so if I say actor Jim Carrey, and I've got the object actor, so I'm saying actor Jim Carrey is a actor, so I've got a -1 we'll just call this an edge here. I've got a -1 here and a 1 here. This edge is defined by the head. Alright, and again, that head in this edge is the actor. So let's give another actor. Let's say actor Jeff Daniels. Alright, so this is defined by actor, so we can just put a -1 here. Okay, and so if we're looking at this edge, we can see that actor is actor Jim Carrey, actor Jeff Daniels is a actor. Let's see, let's have an object, movie, Dumb and Dumber. And that movie, Dumb and Dumber, we'll say is a movie. Alright, and so we need a new edge that's defined by movie as the head. And we'll say movie Dumb and Dumber is a movie. And then we'll say movie Dumb and Dumber has a actor Jeff Daniels and has a actor Jim Carrey. So we need, and this is defined by the tail, so we need a new edge where that is defined by the tail movie Dumb and Dumber, and it has a actor Jeff Daniels and it has a actor Jim Carrey. Alright, so now let's say another property that this movie has. Movie Dumb and Dumber has a director. Which is Peter Farley, just put PF. And so this already, the tail of this already exists, so we use this tail to show that movie Dumb and Dumber has a director, Peter Farley, right there. And so now, again, this edge shows all the properties that the property value pairs objects that movie Dumb and Dumber has. Alright, let's say it also has a writer. I don't know the writer, we'll say John. But I think it might be Peter Farley again. So there's a 1 right there. And, you know, of course, writer John is a writer. So we need another edge here that's defined by writer as the head, and we've got -1 here for writer John. So writer John is a writer. Let's see, let's have another movie. We'll say movie Truman Show. And so we've got another director of the movie. I don't know who that is. We'll say it's Bob. I need more space down here. Director Bob. So movie Truman Show has a, and so we need a new edge because has a is defined by the tail. Movie Truman Show is -1 there, and then director Bob, and movie, it also has actor Jim Carrey. Alright, and let's see, we can say that there's another movie. We'll say Ace Ventura. Alright, and I did forget to say that movie Truman Show, movie Ace Ventura, those are both types of movies, which we've already got this edge here, which is defined by the head movie. So all we need to do is put -1 for movie Truman Show and -1 for Ace Ventura. Now, we could go on and on with this. There could be properties of Jim Carrey. We could put that, you know, that he's got an office address, the person has the home address, the actor has famous traits, the person might have an eye color, there could be a producer to the movies, they can have different actors. So even in that small realm of actors and movies, these matrices will be huge, and they, especially since I propose a knowledge base where there is no domain. The domain is universal, and that I think that's possible because I think using this setup, you can model, you can include any object and have it relate to all the other objects. And so this will easily get to be a very, very large matrix. So the first thing we would need to do in order to make this practical is find ways to partition this matrix. And we could either find partitions based on each one, or combine the two and then find the best partition with that. I would think it's probably better to combine the two matrices and then find partitions, because you're going to want to navigate has a and then see the is a. Such as, we may say actor Jim Carrey you know, has a famous trait, and then has a famous trait rubber limbs, and then famous trait rubber limbs, that object is a famous trait, and then from there we could see all the other objects that are famous traits, and from there we could see, you know, what other objects have on this side have that property of the famous trait. So, you know, I imagine in some application we'll want to parse between, you know, we'll want to see paths from the is a to the has a and back and forth to make it useful. So the point is that we want to create partitions with that are very densely clustered and where the partitions do not cut a lot of edges. And these partitions would allow us to perhaps put different hypergraph matrices on different servers, on different be looked at by different processors, and just have a lot more efficiency because it is meant to be a universal, very large knowledge base. And so that the partitioning of graphs and hypergraphs is a very popular area of research, and it is finding an optimal solution is an NP hard problem. So the best that we can do is find heuristic solutions to it. Of course, there is always the option of just you know, going through every single edge to see what vertices in it and, you know, try to find cuts based that way, but that would take a very, very long time. So the best options we have are to do use heuristic algorithms, and the best one currently being, let's see, it's called the fiducia metathesis algorithm, and it's a heuristic algorithm that keeps moving rows around until we can find good clumps, and then it keeps moving entries around from one vertices around from one partition to another until it finds the best solution it can. And another option might be like a simulated annealing algorithm, where you just make guesses as to partitions of the matrices, and at first you may accept bad guesses that don't partition it well, but over each iteration you make better and better guesses, and you accept less and less bad guesses. And so if we could partition that very large, this very large matrix, the next step would be to parse it. And there's a lot of benefits to parsing the algorithm, finding paths. The first one being that we can make statements, such as saying that actor Jim Carrey has a person, Jim Carrey. Jim Carrey is a person. Another person who is a person is, if we had another Adam here, a person, Peter Farley, is Peter Farley. Peter Farley is a property of director Peter Farley. Director Peter Farley is a director. You know, we could make a lot of statements, do a lot of comparing and contrasting, and see patterns by parsing these matrices. And so algorithms we may want for that are path algorithms, such as Dijkstra algorithm, but for maybe dynamic data. And shortest path would allow us to say, how is director Peter Farley related to the movie Ace Ventura, and find a way to explain the connection there, like a Kevin Bacon algorithm. Another benefit to parsing would be to remove redundancies and to see where redundancies lie. By redundancies, I mean something like, let's say we have movie Dumb and Dumber is a movie, but then let's say we also have movie Dumb and Dumber is a video media. Right, so movie Dumb and Dumber right here is a video media. But then let's say that we say movie, which have we already defined? Yeah. So, no, let's say here. Well, we say movie is a video media. Right, so these two things both say that they're video media. Well, if we've already said that movie Dumb and Dumber is a movie, so it's a bit redundant to say movie Dumb and Dumber is a video media if we're already saying movie is also a video media. So by parsing the matrices, we could see that this entry right here is a redundancy, and it's better to describe movie Dumb and Dumber as a movie, which then itself is a video media. And then, we can parse this algorithm for all sorts of redundancies like that to be able to give very clear, precise information when we are parsing it to make lexical statements. All right, another very useful result of parsing the matrices is to make guesses. And I think that's where the most interesting thing is, especially from an artificial intelligence perspective, is that we can try to find patterns and make assumptions about objects. For example, let's say we've got we have movie Dumb and Dumber, which has director Peter Farley. We have movie Truman Show, which has a director, Bob. And now we have movie Ace Ventura. Well, we've already said that movie Truman Show, movie Dumb and Dumber are movies, and they each have those properties. So it may be a good guess to say that other movies also have directors. And so since movie Ace Ventura also is a movie, it may also have a director. And as we get more information and we see that more movies have directors, it may show us, give us a better and better probability that movie Ace Ventura, it has a director. As it stands right now, what this is kind of indicating is that movies that have actor Jim Carrey and a director movies that have Jim Carrey have a director. So this is actually giving us kind of a weird assumption that Jim Carrey is the key to having a director to a movie, or something like that. But again, as we get more and more data, we'll be able to make better and better guesses. So that's my presentation on hypergraphs, and I hope I've shown why they may be useful, and I hope I've argued that this knowledge base where there are only these two relationships, is a, has a, and the two types of objects of a property value pair and a class of objects, and the constraints on the relationships between all those. I hope I've shown that that's a good model for knowledge, and it's well represented by hypergraphs, and that we now, if I were to ever work on implementing this, we would just need very good partitioning algorithms, parsing algorithms, and if we could, it'd be a very good use for artificial intelligence. And I hope that something like this is already being developed, because I think having some sort of universal knowledge base, like Wikipedia, but in a very in a much more dynamic, intelligent form, would be very cool to have. I think it's especially cool that you can have non-structured data in these very simple statements. Movie Dumb and Dumber is a movie, and just having a series of those statements in a very unstructured way can then, knowledge can then emerge from that. It can emerge from the connections between all that. All right, well, thank you and have a great day.